Hello, everyone. I think we are live. Are we live? Did anyone check?
I'll go check over here.
Yeah. Oh, hello, everyone. I see there are some
I'll go check over here.
Yeah.
Yes,
Oh,
we
yeah.
Happy New Year, everyone.
Oh, wow. Yeah, Happy New Year, everyone. Welcome to
Happy New Year.
MakerCast, the show where makers are sharing their latest creations. And today I'm happy to host some wonderful people that will introduce themselves soon and show a few of their creations. And yeah, I hope you all enjoy. And let's just start. Who wants to go first?
Are we not making the introduction round first and then someone tells?
Okay, yeah. Okay, let's do introduction. Let's start with Tom. Tom, tell us something about you.
All right, cheers. Yeah, thanks for inviting me again. So my name is Tom. You might know me as one of the people in Europe who make badges for hacker conferences, electronic devices that do odd things, like this one right here, playing Nyan Cat. So I've been making these badges ever since getting truly inspired by them in 2017 in the Dutch hacker camp SHA 2017. Of course, in the US, I think badge life has existed much longer, for maybe a decade more or so, and we're catching up in the EU, but we're catching up quite fast, I would say. So in a time outside of hobbies, I work on in the R&D department as a firmware engineer at Ultimaker, the maker of 3D printers. And I also run a company on the side with electronics. And today, I think I will be taking a sidestep away from badges, and we'll be talking about something different. So we'll see.
Okay. Thank you, Tom. Next one on my screen, at least. Let me share it like that. Is Ian. Ian. Tell us something about you.
Wait, I can do my own bio?
Yes, sure.
Okay, I'm 8 feet tall. I have an IQ of 230, and I have never tripped over my own feet. Never.
Okay.
No, those are all lies. I'm Ian Charnas. I'm from Cleveland, Ohio, in the U.S. And my day job is I run a makerspace and innovation center called ThinkBox. It's associated with Case Western Reserve University. It's a very large space. It's 50,000 feet. It's a $50 million project. So we've got a metal shop, a wood shop, 3D printing, laser cutting, a water jet cutter, electronics, textiles. And it's free and open to the public. So if you're ever traveling through the US, through Ohio, stop by ThinkBox and come make some cool stuff. It's totally free to use. The trainings are free. Very cool space. But on nights and weekends, I make silly, funny inventions on YouTube. And I usually raffle them off then for charity. So I've made a nuclear-powered Game Boy. I've got over here, there's a jetpack that I put on and to see how fast I could roller skate. Spoiler alert, not that fast because I'm very clumsy. Right now, I'm working on some cool projects that I'm excited to be sharing with you all today. So I'll leave it at that for now.
Okay, thank you, Ian. Right here, next one, Usagi Electric, David. David, tell us something about you.
Yeah, hello. My name's David, and I guess since we're introducing our day jobs as well, my day job has absolutely nothing to do with electronics or making or anything like that. I'm actually a technical translator from Japanese to English in the automotive sector. And I've been doing that for like 15 years. But that sounds really cool, but it's very boring. And so to keep myself entertained, I'm sometimes better known as the tube guy. I'm actually wearing a shirt with a vacuum tube on it. I got obsessed with vacuum tubes about, I don't know, a year and a half ago. and I just kind of losing sleep at night thinking of things to build and do. I built a lot of kind of interesting things. I have some audio stuff. A couple of MakerCasts ago, I showed a vacuum tube-based 555 timer that I built, which was kind of fun. And then today I have something that's rather large to show. I mean, vacuum tubes inherently are large, but this is exceptionally big. So I'm looking forward to showing that off. So that's it. Thank you, guys.
Okay, and last but not least, Dave Darko.
Yay. So, hi, I'm Dave, and let's see, I'm going with the self-made titles now. I'm calling myself the community manager of the Exine Hackspace that I'm a member of, but only the electronics part. And I'm just trying to gather more and more people that work on electronics and overlook when they, I don't know, bring a project and maybe need some help that I can connect people. And then I also like to tinker with electronics and design badges or interesting electronic things that I will later regret that I have to design it and program software for it. And my day job was way too complicated to explain, so I'm not doing that. And that sounds more mystical than it actually is.
Okay. Thanks, Dave.
Now I really want to know. To LinkedIn.
Well, I don't think I'm on LinkedIn. I might be on LinkedIn. I'm not sure if it's up to date.
Okay, so what is it, Dave? So you're a coder or?
Okay, I'm a software developer, and we basically built our own shop system with ticket system for wakeboarding and water skiing parks. So there's also some hardware involved where I do some Arduino projects that basically allows people to just scan in, and then their ride starts, which is basically like an hour ticket or 2 hour tickets. And then we made some other weird designs, like a for lockers when you scan in and you have something reserved that opens up for you and stuff like this.
Okay.
Yeah. But.
Cool. So we are showing off stuff today that we made. Tom, will you start? Like.
Yeah, sure.
Okay.
Absolutely.
Okay. Can I leave it like? How do I pick someone here to? This is.
There was something you have to do this, and then you can, I think, drag and drop the person you want to see.
Oh yeah, okay. Oh yeah, that works. That's cool. I have the duck on my screen.
All right. So the previous time I was on here, I showed some badges. I have many of them. Today, I thought it would be nice to talk about something different. So instead, we'll talk about security adjacent projects. Some of these are completed. Some of them are in the progress. So I have a few in mind, and we'll see where we end up. Okay. So the first thing I want to talk about is this. This is the remote for newer key lights. These are the suns shining in my face right now from the side and the front. And these are really nice lights. They're very affordable. I think they're half the price of the Elgato key lights that are very popular with streamers. Very nice to use, but they have one flaw. And that is that this nice remote that they have does not remember the settings that you set the lights to previously. So every time you want to power them up, you have to click 19 buttons to individually set each of the lights to the brightness and the color that you want. So I was thinking probably this can be improved. And so I went on a quest to find out. And of course, the first thing you do when you go on a quest to find out if something can be made better, you unscrew the thing, you disassemble it. And I found that this controller has a well-known STM chip in there, an L1 series. And I thought, haha, I am in. This thing we can program ourselves and then make it do whatever we want. But alas, the Chinese developers had thought of this already, and they locked the chip. So you cannot read the contents that are on there, and you cannot write your own. So that plan was foiled. There's actually a really nice write-up. I forget by whom. It could be Travis Goodspeed, I'm not sure, on how to break security of specifically these chips. So when they're locked, you cannot read them and you cannot write them. There is a trick to unlock them, but it's quite complicated, so I didn't do it. Instead,
what is the trick?
I think it's a voltage glitch attack.
Oh, okay.
So where you expertly drop the voltage of the chip at the precisely the time where it checks if it's locked or not, so that it skips over the check, but does continue executing afterwards.
Oh yeah, we saw that hack by Aaron Christoffel for hacking some security before. I think he even showed that on some kind of MakerCast. So it's the voltage glitch. Nice. And
yeah,
you
so
did it a different way. Yeah.
Voltage glitching has been used in a bunch of really cool hacks. I think also the PS4, the first exploit for it by George Hotz, I think, was also a voltage glitching, and many game consoles and lock devices and such have been broken that way. It's a really cool attack. So anyway, I didn't do it. Could have done it, didn't do it. Instead, I looked at the chip that it's connected to on this board. This chip here is a clone of a Nordic chip, the I think N24R1, and this is a chip that provides you wireless data transmission, much like Bluetooth and Wi-Fi and that kind of stuff, but using their own protocol. And so I figured, okay, so I know what this chip is. It has a public data sheet. We can look into how to configure it, how to send data to it, and stuff like this. And the microcontroller on this should some way communicate this data into the IC, right? The transmission IC. And since this transmission IC has a very nice datasheet online that explains exactly how to talk to it, everything that remained to do was to hook up some wires to the microcontroller that talks to this IC and connect the wires to a logic analyzer. By doing that, I could dump the way that the microcontroller set up the IC, so how it configured it, what frequency to use, what sort of form of data packets it should send, whether to acknowledge data or not acknowledge data, these kinds of things. I was able to completely dump the thing, found out the protocol that it was using to talk to the lights, and then I was able to replay these commands. I bought an RF Nano. So this is an Arduino board, like the Arduino Nano, but it has this Nordic chip already installed on it. And with some simple code, I could replay the commands from the remote, and you should be able to see, ta-da, lights going out and on again at precisely the settings and things like this that I want.
Nice.
So that's project number 1. This is written up on my blog in the name of science.nl, and you can read all about it. I think actually Dave bought one of these lights too, and found out that more recent models, or different models anyway, use a different kind of chip. So perhaps the blog was useful to him, perhaps not. Okay, so that's project 1 I wanted to talk about, and if I have a few minutes left, there's project 2 as well.
Sure.
So in the Netherlands, we have these Wi-Fi connected light bulbs from a company called LSC. But these light bulbs are actually not from the company called LSC. They're from a company called Tuya. And Tuya is a Chinese manufacturer that makes a gazillion different types of smart IoT devices. And they sell them as sort of white label things, so you can put your own brand on it. And of course, every country has some companies that do this and make their own smart IoT Wi-Fi lamps. Now, these things are really cool because they're very, very cheap and very useful if you run your own software on it. If you make firmware for these things yourself. And they used to contain a very popular microcontroller, the ESP8266, which was very nice because people were able to reflash it, run their own firmware on it, and then you can hook it up to home automation stuff, like a home assistant and these kinds of things. To get your own firmware running on these light bulbs, you have to flash your own firmware, and this is prevented from Tuya, from the manufacturer. So previously, people found security exploits in the firmware that was running on these things out of the factory, and exploited them in order to write their own firmware. And at some point, Tuya thought, oh, that's bad. This is a security exploit, so we have to patch it. And after that point, all the new light bulbs that were created were not routable anymore. You could not write your own firmware to them. So together with a friend of mine, Khaled Nassar, we've been bug hunting these new firmware versions of the lamps to figure out if there's some new exploit that we could use. And we found one. We were not able to exploit it yet, but there was a really nice buffer overflow in the software, so where you write far longer into the memory than the thing you're supposed to write in is actually sized. You overwrite a whole bunch of data. And so we were really happy about this, and took us a long time, but we were very glad to find something. And then they, Tuya, the creator of this, they put a new chip in the new lamps. We bought some new ones from the store, and they have a completely different chip in there. And so we thought, oh no, everything is lost now. We can start again. But in fact, it turns out that this was a kind of a big win. I'll explain why. So the new chip that is on here is a very neat one, made by a company I don't know, and maybe you don't know either. It's called Beacon, a Chinese manufacturer. This chip is the BK7231T. This is like the ESP8266 in that it has Bluetooth and Wi-Fi, and you can run a lot of code on there. It has built-in storage, that kind of stuff. But it's an ARM controller. And so the software support for these kinds of things and the tools you can use to debug them are much wider than what you have for espressive chips. And so now we have a much more capable chip on this, which we can debug much more easy. So there's devices you can attach to this chip to debug them in hardware. So to stop anywhere in the program, see where anything in the memory is, that kind of stuff. And as the cherry on top of this, Tuya, the company behind this, also open sourced the software that's running on this. So not only can we now debug and find out actually where the bugs really are and try to trigger them, but we can also do sanity checks in the source code at the same time. So this is an ongoing project. We're working on it. We've again found something that could be wrong. Could be a software bug in there that could be used to write your own firmware into it. And we're checking it out now. We're setting up the hardware for everything for debugging it. So more progress on this at some point in time.
Where can we find something about this project? So where can we read or link or something?
Yeah. So with security things like this, you have to follow what's called responsible disclosure, which means if you find a security bug, you have to report it to the manufacturer and give them some period of time to fix it before you make it public. And so there will be a write-up on this, on what the bug is, and also how to use it to write your own firmware to these lamps. But of course, it has to be after this period. Before then, we cannot publish anything. Then Tuya will get mad, and probably rightfully so. So we will do a write-up on this, and you will hear about it if you follow me on Twitter, for example.
Okay, so the links are in the description of all the people that are on the stream. So check out Tom often to see on the progress there. Thanks. Anything else from you? Or?
Oh man, I have so many projects to show, but I think we should probably hand it over to someone else. Huh? You can come back to me if we have time.
We're still fine. If maybe we do another one later. Okay, so Ian, are you ready? Are you ready to amaze us?
Yeah, well, I'm ready. Those projects are awesome, Tom. I love those. I'm just meeting you for the first time, so I'm going to go check out your channel after this.
Oh, Tom is only on Twitter, so he doesn't have a YouTube channel.
Oh, that's even easier then.
Yeah, you can read
Why is he in here then?
during your commute. Yeah.
I'm kidding.
Yeah, I have a few. I have maybe 2 or 3 projects. I'll just share them really quickly. I'm going to try to share my screen. Bitluni, let's try this. Let's see how.
Yeah, here we go.
Oh boy, here it goes.
Docs. Wow, we see your file system. Oh, okay, here we go.
Okay, so the first for the first project. Oh wait, can you stop the screen share? I should introduce this first.
Yeah. Okay.
Also, maybe minimize the window so people don't come in here. You've shared the link.
Sorry. What?
Oh yeah. Minimize the
Never
window
mind.
of your.
Of the StreamYard.
Yeah. Okay, but I have control over that, so no worries.
Thanks,
Ian.
So I got contacted by a Canadian YouTuber named Tyler Satari. I hadn't heard of Tyler Satari, but he's one of those guys that does these physical challenges. So he did 1,000 push-ups in one day, and he's done. He has a video where he did 50,000 sit-ups. Maybe you can all do 50,000 sit-ups like it's no problem, but for me that's really impressive. And he actually does them. It's not fake. So here's what he wanted. He does these physical challenges, and he wanted to be able to jump really high. So he had this idea for pneumatic jumping shoes. He's not an engineer, and so it's an idea, and it can be interpreted in many different ways. So I was like, okay, you want to be able to jump really high. Let's look into that. And I pitched him on a couple different ideas. What he was imagining in his mind was like pistons that would push down into the ground. And I thought, we can do better than that. So I looked into this, and it turns out that in the stunt industry, people who perform stunts for movies, there's this thing called an air ramp. And it's basically a hinged board that has a hydraulic or pneumatic piston that actuates it. And over the course of maybe 2 feet, you would be accelerated, and then you would launch through the air. And you can get 10, 15 feet up into the air. It's pretty impressive. But he didn't want to do that. He wanted shoes. So I said, okay. So I briefly looked into chemical propellants, like the chemical that's inside of airbags, which very rapidly expands. But I would basically be putting explosives onto his feet. And my lawyers told me I shouldn't do that. I have no lawyers. I told myself that I should not do that. So I looked into a couple other options, including putting small jet engines on his arms so that he could push off of them, kind of like using Olympic rings. And then there's also something called kangaroo shoes, which is a product you can buy. So I kept pitching him these ideas, and he really didn't like any of them. And I said, okay, what about hydraulic or pneumatic pistons that push into the ground? And he liked that idea. So I started designing it. The basic idea is that I got, I instructed him to buy these special shoes. These shoes are for construction work, and they not only do they have a steel toe, but they also have a steel shank in the bottom, like the sole has a thin piece of steel in it. So I'm going to attach, this is not the final product. This is just me messing around really quickly. So I'm going to attach some brackets to the bottom of the shoe and also to the top of the shoe to clamp this in. And then there's these this is so goofy. These pistons are gonna push down. There'll be 2 on each feet. If you have 100 psi in this piston, then it will push with 177 pounds of force. So with 4 of them, we'll get about 700 pounds of force. And I found these really convenient little bumper feet to attach to the bottom, which have, oh, you can't see that. They have a good amount of grip. but they also withstand impact. So I'm going to put these on him, and then now bitluni, can I do the screen share?
Yeah.
And I'll change my screen.
Here you go.
Am I sharing now? I can't see.
Yeah, you are sharing now. Yeah.
I'm a one monitor man. So this is the part that clamps onto the feet. This is so goofy. And then you also need a source of air. So this is a big it's a spun aluminum tank. And then there's 4 solenoids because these are two-way pistons. So two-way pistons meaning you use air to expand and you also use air to retract. There's no spring return. And that's on purpose because I want this to return really quickly. And then there's a battery up here. And then for the switch, okay, now I can stop sharing bitluni.
Okay. Here we go.
Okay. For the switch, I'm using one of my old tricks, which is to take a drill body, and you just take out the motor, and you can use the switch. So he's going to hold this in his hand, and basically he's going to jump, and then right when he's about to leave the ground, he's going to press this button, and the pistons will shoot down with up to 700 pounds of force, and we can slowly increase the pressure as we're testing this thing. And we're going to see what happens. According to my math, he should be able to get maybe 3 or 4 feet up into the air. Or if we turn the pressure up to the burst rating of of everything in the system, he might be able to get up to 5 or 6 feet up into the air, which is what he wanted. He wants to be able to dunk a basketball, maybe do a high jump. This thing is super goofy. I actually don't know if it's going to work at all. He's going to have to time this like perfectly. But for me, the most interesting part was trying to get an understanding of the safety of this. Like, how much force can you put on someone's foot without breaking their ankles? And it turns out that science has already looked into this. There's a field of research that they use in sports, and it's especially popular in European football, which in America we call soccer, players. They want to reduce foot injuries, especially when there's jumping or kicking. And so they have these athletes jump and land on this sensor called a force plate. And it turns out that when you land, you usually land with one foot first, and it's a very light amount of force on that foot. And then your second foot comes down and really takes up most of the force. And that force can be up to 17 times your body weight. So if I weighed 150 pounds, which I weigh more than that, so thanks COVID, then 17 times my body weight would be 2,500 pounds, which is like a crazy amount of weight. And I wanted to keep it much, much less than that, even though he's very fit and does these physical challenges. He's not a professional athlete, and I just don't want to end up in the hospital. He is Canadian, so he gets healthcare. I would be more concerned in the US where I would say, okay, what kind of health insurance do you have? Or where's the nearest hospital? But he'll be okay. He's 22. He's invincible. Okay. But really, we're going to be that. So we're keeping the force low, a quarter of what the professionals can do. And also, we're going to slowly increase the air pressure as we go. But I'm curious now, before we attempt this, does anybody have any guesses as to like, is this going to work? Is this person going to get injured? Was there a better way to do this?
I think this is like, it's a thing of practice, because what you said, if you like landing in the first leg is like giving only slight force and the second catches the whole body. It's basically, I think, what we learned to sense when is the ground coming, to like tension the muscles on the other leg to like catch the weight. And this is something what you don't have if you trigger it. You have to like connect this like hardwire first, like your trigger or your will to perform this jump or whatever you want to do with the actual like trigger of the pistons then.
Yeah, timing will for sure be interesting, huh?
What's the headline going to be in the online? part-time YouTuber breaks full-time YouTuber's ankles. I really don't want to hurt this guy. He's a really nice guy, so I'm doing everything I can to think about safety ahead of time. We're doing this in a gym. We're going to have some crash bags. You know, like in gymnastics, there's like a soft foam mass that you can land on. So I'm doing all of the things I can think of safety-wise, but we'll see what happens.
I'm curious about timing between left and right foot, because you have 4 pistons, right? If the foot triggers like whatever 100 milliseconds after the left foot, that's a noticeable shift in energy, right? Yeah.
You could go sideways.
Yeah. So like, is there like, how are you going to handle the timing issue?
Well, first, I'm concerned about that. And so we're going to have these like crash mats all around him. I'm imagining like just like a 2 by 2 foot like square of gym floor that he's standing on. And then all around him are these crash mats or mattresses or something. And we start off at just, 20 PSI, 40 PSI, 60 PSI, so that we can kind of slowly get the hang of how dangerous this is. But he's going to like lean forward with his whole body, and then he's going to, like if you're jumping on 2 feet, you kind of bring your arms down and then jump. He's just gotta get it really good. I'm doing all I can in terms of safety, but there's an amount of coordination that is going to come into play.
I mean, you survived your jetpack, so it will be fine at the end.
The jetpack sounds more dangerous.
Ooh, can you combine them?
Yeah, I wanted to give him a jetpack. So with these jetpacks,
so whoever didn't see that video of Ian using his jetpack,
so this is the jet engine.
And subscribe.
These are something you use in radio-controlled airplanes. If you have like more money than brains, you can spend $10,000 or $20,000 on a radio-controlled airplane, which I guess is okay. Like if you're going to have an expensive hobby, have an expensive hobby. But this one can generate 30 kilograms, 66 pounds of thrust. So if you can imagine having, oh man, this is heavy. Yeah. If you can imagine having 1 or 2 of those on each arm, and they're positioned like they're pointing downward, you should be able to push down with enough thrust to make you pretty much weightless. And then if you jumped with your legs, it would be like jumping on the moon. You would like slowly go, as high as you want. That's what I would really like to make for him. I think that would actually be safer. Because there's less pressure on his feet. Like our ankles are like the wimps of the body. So I'm really worried about his ankles. We'll see what happens.
Like very, very strong shoes. I think the knees might be the problem. They are like buttery soft and will like hopefully bend in the right direction.
Yeah, I got the tall boots, and these are really stiff. Yeah. So I think this will help. But yeah, maybe something for the knees.
In cross motorcycling, you have these plastic boots that go almost up to the the knee, and they don't bend at all. So if you exert, boots? yeah, but so fully hard plastic. Yeah. And so if you exert pressure on the front of the foot, it doesn't bend the ankles and stuff like this.
Yeah, it sounds like ski boots. So.
Yeah, same.
Oh, that's interesting. So you do need a little bit of flexibility, because the next time you jump, look down at your feet, and you'll see that you jump off of the ball of your foot, like right here. And in order to jump decently high, you have to be able to flex your foot a little bit. So it would be hard to jump in ski boots. Well,
but
let's just
that's a trade-off. That's a trade-off. You could, with ski boots, you don't have to worry about the weak point of the body, so you can crank PSI up to compensate, right? Just go full set.
Yeah, just go immediately up to 200 PSI. Don't even worry about it. Yeah, then the knees would be the weak point.
Okay.
So my next project, I've been talking with a YouTuber in Florida in the US, and he does quadcopter drone type stuff, like first person view flying. The channel is Rotor Riot, and it's pretty cool. They have like really beautiful drone and quadcopter footage. And I wanted to design him like a weird quadcopter. And so what I came up with, bitluni, can I share my screen again?
Ooh. Just 1 second. I just saw someone ask in the chat. It's David Watts. He's asking how the person would land with the pistons out.
Oh, the pistons will retract almost as fast as they will extend. So he's gonna provide some. That's a really good question. He's going to provide some upward force. The pistons are going to provide extra upward force. So let's say he goes up into the air 3 feet. As soon as he lets go of this trigger, so he's only going to momentarily click it, and maybe I'll add a micro so that it's more automatic and he doesn't have to time it. Then air will be forced the other way because they're 5-2 valves, two-way valves with 5 ports on them. Air will be forced the other way, and it will force the pistons back into their retracted position. At which point, see if I can do this. At which point they are above the point of the bottom of the foot. So they should retract faster than it takes for him to land.
Okay.
If that makes sense. That's a good question. All right, bitluni, am I sharing my screen?
Yes, we can see your screen.
So there's this, if you were a fan of YouTube and science in like the year 2005 or 7, you would have seen a lot of videos of this. This thing is called a lifter. This guy named Roger Beefield back in like 1920s or 30s, he discovered this effect where you take a piece of aluminum foil and let me stop right here. So this part here is aluminum foil, and then if you can see it, there's a very, very thin wire strung across the top, and the frame of this is made of lightweight balsa wood. So the idea is that you apply 20,000, 40,000 volts between this, what we call the corona wire or emitter, and what we call the grounder collector, the aluminum foil, and it generates a little bit of thrust. And Beefield thought that he was defying gravity. He thought that he had discovered an anti-gravity device. And since then, we discovered that all you're doing is creating a little bit of ion wind. Like you're ionizing the air, and then the same electric field is pushing the air downward. So not only can you feel, I mean, you can feel the air, it's really obvious. But if you used a smoke machine, you would see that the smoke funnels down to the center of this thing. But it does produce thrust. So this one here produced about 4 grams of thrust. And what I've been doing, now I can stop sharing my screen now, bitluni. You're really being a good sport about this. So I did a set of experiments where I tried different geometries, different materials, and I found that if you use an airfoil section, and if you have it longer, and if you use stainless steel wire, I'm able to generate, with this, I'm able to generate 10 grams of thrust. So my idea is I'm going to make 10 of these, and it'll be like a big box. You can almost imagine like a big louvered panel, like an exhaust on a building or something. And they will provide in total 100 grams of thrust. So I'm going to make 4 of those, because it's a quadcopter. And the idea is that the high voltage power supplies and the batteries will be held aloft by a helium balloon. And then down below, this like ion thrust quadcopter will steer this thing around the room. And it will be really cool, and it will kind of glow purple in the dark, and it will move really slowly. So it's going to be a challenge to fly because you're going to want to fall asleep.
but that's such an amazing idea, I really like it. It's very creative and using so many things that are interesting in itself. Yeah, definitely.
I think it's a good opportunity to talk about the science. Now, here's a question, because you guys all make content. Should I call it anti-gravity quadcopter? Even though I know it's not anti-gravity.
Oh yeah,
just
go
use
for
that
it.
as
Definitely.
an exciting title.
Don't,
or should
don't
I call
let,
it ion thrust quadcopter?
Don't let only the drugs exploit clickbait.
Okay.
Yeah. Maybe add something, a secret from 2009 finally revealed or something like this. Like, we've had this technology for
Nikola
10 years,
Tesla
but
knew
finally.
about this.
Yeah, free
Nikola
energy.
Tesla secret revealed.
Oh, you're talking like Tesla 0-point energy, free nuclear, .exe.
Well, that's good enough for the text, I guess. But yeah.
Should I show one more if it's quick?
Yeah, sure.
Do it.
Okay. Can I share my screen again?
Yes. Are you ready?
Yeah, I'm ready.
Okay, here you go.
Am I doing it?
Yeah, you're doing it.
Okay.
See YouTube.
So I discovered this thing called rocket triggered lightning. And if you can see this little dot moving up and down, this is a model rocket, and it has a very fine copper wire attached to it. And what happens is it goes up into the clouds, and under the right atmospheric conditions, this happens.
Oh, shoot.
So you created a conductive path between the Earth and the thundercloud, and it makes it lightning. And I really want to do this. So most of the research is conducted in just a couple areas. There's
Kids,
like Florida.
Please don't do this at home.
Yeah, don't do this at home.
Let Creo-san do it, or Ian, but not you.
So there's a couple phases to this. Number one, I have to figure out like where does the lightning happen. So I found this worldwide network of lightning sensors, and their security wasn't that good. So something, and now I have access to the data, and I've been plotting the data of like where lightning strikes happen near me. So I live here in Cleveland, and what I want to find out is there a pattern to where the lightning appears? And especially, is there lightning like near a farm or a big field, so that I can go and actually try this? So step one is finding a location. Step two is you can't just shoot the rocket at any cloud. It has to be an anvil-shaped thundercloud, and you have to have a certain electrostatic field gradient in the atmosphere. And so you need something called an electric field mill to measure that. I don't have one of these, but if anybody wants to buy one of these or make me one of these, I would really appreciate it, because that will help me get the lightning from the cloud.
Can't you just measure a gradient just with a stick pole or whatever? Like a stick with a probe or something, and just measure the difference? Because I think the potential will just rise when there is like something coming. So you will see a higher difference in voltage. You have like this voltage difference in altitude. And if you just take a 5-meter stick and have like the probe on your voltmeter, there you will see maybe the voltage difference is rising when there is like some tension.
Yeah, see, I thought that too. And then I looked into it, and I tried it, and I discovered that if you have a long stick and then a wire coming down like to a voltmeter, and also another probe coming out here, those two probes will quickly come to the same potential.
Oh, okay.
Because it's electrostatic, and these things kind of will tend to start to equalize. What this does is this field mill, it covers and uncovers a sensor.
Oh, okay.
And so you get you're able to kind of get an AC view of things, and that is what makes it work. I don't understand that 100%, but maybe someone else who knows a little bit more about electrostatics can explain why that works. So I can stop sharing my screen now.
Ian, does the lightning bulb actually come down via the wire, or does it just hit in the vicinity?
Well, first, first a small lightning bolt comes down and vaporizes the wire, and that's why it looked so straight. And then the second thing that happens is you have a carbonized path of air, and now you'll have follow-on lightning. And this is where this is what's really cool, because
Plasma
the initial
is conductive, isn't it?
Yeah. The initial lightning strike will only be a few hundred amps, like 300, 500 amps. And then the follow-on lightning strikes, those are the ones that are 10,000 amps, 50,000 amps. But it kind of makes you wonder, can I capture that first strike? Like, I can make a pulse energy capacitor bank that can capture 500 amps. That's not that many. 50,000 amps, no thank you. So I would need to capture the 500 amps, and then it only happens over the course of about 50 milliseconds. And then I would need to like remove the lightning rod or something so that the follow-on bolts won't hit my capacitor bank, because they would explode it instantly.
So
but can you capture lightning? That's the video.
Yeah, or how to recharge your Tesla Model S in 5 seconds.
Or how Ian stopped breathing. You know, it'll be one of those.
Okay.
Man, these are some really nice mad scientist projects, I gotta say.
Thank you. Only the finest for you.
Okay. Anything else, or?
No, I yield my time.
Okay.
So, just a question for the lightning thing. Do you have any franchises that you want to combine with that?
Go on, tell me more.
Would you rather, I don't know, put a little model of a little thing with a clock in there? In the
Back to the Future.
Lightning hits, right?
Oh.
Or you could go back to the Thor thing and then just say you created lightning.
Yeah, that's
what Thor hammer.
So I made
built a Thor hammer that ejects the small rocket.
So I made this Thor hammer. It's 3D printed, and then it's electroplated in nickel. And then I hit it with like some Tesla coil music from the Tesla coil group that I'm in. And the comments that people said, a lot of people said fake, or they called it like really bad CGI. And I was like, it's real. How do I convince you it's real? I could reply in all caps like, no, it's real. But, you know, so I thought maybe with lightning, maybe that would appear to be more real. I don't know.
I don't think you will get people there, because it's that straight. So people will think that's a lazy line in photo editing or video editing.
It's lazy CGI.
Yeah, it's just a line.
Your camera is too good. You need like a really bad camera for it to look authentic.
Yeah,
you have to shake the camera so people can say, that's just bad tracking.
Yeah, it should look like the Blair Witch Project.
Yeah.
Okay, let's go with David next.
All right, so I gotta follow crazy mad scientist with Thor's hammer. That's a tough act to follow.
Don't sell yourself short there.
I'll do what I can. All right, so I guess the story starts, I don't know, a year ago or so. I got obsessed with Ben Eater on YouTube. He made a fantastic series of videos where he builds an 8-bit computer from scratch on breadboards. I guess a processor would be a more appropriate term, but he's really fantastic at the way that he presents it and everything. And I was going, I want to build that camera ever come back. My camera's being off. Go. I was like, I want to build that, but I don't want to build that. You know, it's already been built. So I thought, why don't I build it out of vacuum tubes? Because I have this unhealthy obsession with vacuum tubes. And I quickly realized that vacuum tubes are big for a reason. Vacuum tube computers often build rooms or buildings, and there's a very good reason for that. So, like, even a vacuum tube computer that filled up a room is not as powerful as the breadboard computer that Vinny built. So I'll try and share my screen here. I'm going to do it through Yes, we'll see if we can get this to work. All right, hopefully you guys are seeing something that looks a little interesting in the face. This is a block diagram for a chip from the 1970s that Motorola built. Or are we showing it?
I think you're showing the wrong monitor, maybe? You're showing the StreamYard link and your StreamYard view.
Different monitor.
All right. I don't know how to make any of this stuff work.
Okay.
It's
yeah, it's custom to dox yourself on my streams.
Yeah. Somebody was asking if you're running your webcam on tubes too, because it's a bit choppy.
No, that's just amazing, amazing country internet. Can you guys see that now?
No, it's the wrong screen.
All right, whatever. I'll just have to use my wordy word.
So in the
you'll just have to look at my beautiful face here. So in the 1970s, Motorola designed a chip that was built around the idea of replacing relay ladder logic that was used in industrial systems. The chip had quite a lot of functionality for what it was. The chip was called Motorola MC14500, and they marketed it as a 1-bit microprocessor. And I was like, yeah, Gamebusters, there you go. 1-bit data bus. That's what we're all about. But the chip had a couple of limitations. Because it was meant to do industrial applications, it had the idea behind the one was that you would receive an input, you would do something to that input, and you would sit out just 1 bit at a time, and you're controlling, relays or stoplights or whatever. But for general computing, it had a limitation in that it didn't have arithmetic logic unit. It just had a logic unit. So I took a look at the instruction set, and I said, you know what, it has these 8 instructions for logic. Let's redo that, try to get stuff an arithmetic logic unit there. And so I went through a lot of redesigns, and I came up with a design that was based heavily on the MC14500, but was my own design because it had arithmetic capability. And that is this monstrosity here. I had problems trying to set my camera up because it is so large that I have a hard time fitting it within the frame of the camera. So what you're looking at is 190 vacuum tubes.
Just one little interruption. Yeah, you're already chopped up with the audio, so maybe we can turn this off and bitluni can share some pictures. I don't know. Do you have some pictures somewhere of that thing?
Let's just hold it still for a second so we get more detail in the video. Yeah.
Don't move.
Oh yeah.
Okay.
We can see the tubes, so I can see the tubes. It's a little
Great.
bit choppy.
Sorry for the interruption, but it's hard to understand you acoustically. So, yeah.
Yeah. All right. So, hang on. Maybe let's cut to somebody else, and I will turn off everything in the house, and maybe I can get a little more bandwidth.
Okay. We can try that, but yeah. Okay. So we will come back to this huge tube computer, and Dave Darko will take over for now.
Oh.
Yeah.
Okay. So that's my fault, I guess.
Yeah.
Okay. So maybe let's do this. Okay. So yeah, we always talk about the last month and what we did there, and so I have to basically, admit that I wasn't at home and couldn't really work on anything that I had already here. So of course I started like 2 or 3 new projects, and one of them is inspired by this over here. Oh wow, I was so close, and then I'm not sure if you can really see it. I could move it. Should I bring it over here? Oh, we could also try with my cell phone, and I can go over there. But it's basically a super cluster computer. I think that's the name. But it isn't. It's just LEDs that are blinking. And let me start Discord on my phone so I can enter the StreamYard thing. And this will totally work. That's the StreamYard link. But yeah, it was a friend of mine from the Hackspace sphere. He was sending me a link like, hey, have you seen the latest bitluni thing? I think I have to build something. Sorry, not bitluni stream. I stopped thinking about it after the B. It's actually Big Clive. I'm sorry.
Oh yeah.
And
there we go.
yeah, so Big Clive is a huge fan of those super cluster computer displays. And mute. Okay. I'm in.
Okay.
And I'm pretty sure I muted this. Okay, this is voice.
What are you trying to? Oh yeah. I add you. Add you here. Okay.
I'm moving very slowly.
We have a second camera. Ooh.
Yeah, I thought this was the easiest way. So these are 200. I forgot 271 LEDs. I think you can switch over to me again. Yeah, because it's a hexagon-shaped thing. Anyway, can you? I don't want to make anyone seasick more than I just did, but I will point this at something else so you can leave it in here.
I can remove it for now.
Okay, yeah. So, yeah, when I saw this, I ordered the PCB in the Tindy store or Etsy store by the person that made the PCB for that. And then I ordered like 300 blinking LEDs. And yeah, that kind of got me hooked as well. So I was just designing something smaller with SMD LEDs. And then I was like, well, I used KiCad for designing the PCB, and I just used 2 LEDs and 2 resistors, made some arrangements, made a 4-layer board, and every power supply had its, ground and VCC and the other VCC because I wanted to use 2 blinking colors. They all had their own layer, so I just had to add a wire, and then everything was connected, basically. And I don't know. I'm sorry. I was distracted by a chat window just opening it. Anyways, yeah, that was kind of cool. So I designed the board when I was in America visiting my sister and niece. And then I also started to work on, another LED project. So 2 years ago at the Chaos Communication Congress, there were people that brought an LED cube with, I think, 64 by 64 LEDs. And one of those people was Greg Devil, pretty cool person to follow on Twitter. And he also brought a, what's the English word? Icosahedra? I forgot. It's like the 20-side thing with triangles. Bitluni, you're muted.
Dodecahedron?
D20.
No.
Just say D20.
Yeah, exactly, the D20. So Greg Devil brought the D20, and when we were there with the Hackspace, we also made a big installation of a dodecahedron. And so 2 years ago, I was like, I should totally make an LED dodecahedron thing where every side has some LEDs on it, and then you can display something on it. So yeah, of course, like every project, I sometimes never start it because it's too much work. And but since I was on vacation and I didn't bring any hardware projects with me, I had the time to just design something for 3 weeks. So I thought, yeah, why not tackle this? So this time I started to design my pentagon-shaped PCBs with LEDs. And I found a cool way, I think, to align all the LEDs. And yeah, no, I think that's a bit too much. But Anyway, I designed the PCBs. The dodecahedron is made out of 12 pentagon shaped, and yeah, it's pretty wild to put it together, because I was also looking into how to design a dodecahedron in 3D, so I had to find out the correct angles between the pentagon shapes, and this is the current state of my project. And I've basically glued it together with hot glue on a very shitty 3D print, and I'm now
turn it on. Turn it on. You have the OP1? Is this the OP1, or how's it called?
Yeah. No, I haven't paid that much money to buy an instrument that I rarely use. Yes. I have to be careful. There's my key below it.
Oh, wow.
Oh, awesome.
That's really cool.
Yeah, so I managed to finish 6 PCBs. And yeah, it's very small, and I still have to modify, I think, how many is it? I'm thinking I have to, I have to modify
6
9.
PCBs are enough for YouTube. Nobody will see the backside.
Yeah, exactly. I should get all the credit by now. I'm sorry for the shaking, but
that's how we know it's real.
I have to turn it off for a second, and maybe you see the botch there.
It's a little bit out of focus, but I can see a blip there. Oh, so, yeah. There is a small wire, like really tiny one.
When I designed it, I didn't run the not design rule check, but the other one, the one that you're using for the schematics file. So it would have told me that one LED has no connection for the common anode, I think. Or cathode. No, cathode is a positive one, or is anode the
anode?
Anyways,
I think is positive.
Yeah, so I had I had to basically make a connection from one LED to another one with magnet wire, and it's very thin magnet wire, which is kind of annoying, but yeah, it worked for the 6 PCBs, and it will for the other ones. And I also had to botch 2 other power connections because I followed the data sheet and never really noticed that the battery and the VCC should be the same, so they weren't connected. And of course, the shutdown pin was connected to a microcontroller in the application design thingy. And yeah, I never really noticed that I have to pull it up, so it wouldn't turn on in the first.
That was a lot of debugging, I imagine.
Yeah, but I was very lucky that someone found, someone basically ran into the same problem, and that person was posting on Hackaday.io. So yeah, I just read it and was like, oh no, I knew it. I did the same. So yeah, but when this was all done, yeah, it was basically working.
Dave.
But yeah, that's a very good question.
Did you find a good way to get the enamel off of magnet wire to make the connection? I've tried many things and they're all bad.
I just used fresh solder with the resin core in there, and that kind of melted it at one point. Can we switch to my camera again, because I'm almost cramping up with my hands?
Yeah.
Thank you.
Yeah, here you go.
So,
I just turned it off again. Here we go.
Yeah, thank you. I might show something else, but I see a question, or I saw a question in there. I completely blanked.
Is it like, I don't know, it's somehow...
No, I forgot Ian's question. Did I answer it?
So Ian's question was, how do you get the enamel off wire? And someone in chat says, rightfully so, also you can burn it with a lighter or some other source of fire.
Yeah, I just completely blanked.
My soldering iron with a solder blob on the tip, and just push the tip of the wire into the solder blob, and it has to be around 400 degrees where the protection burns off. So And the other question was if it's one of the addressable LEDs, but somehow I lost that comment. Yeah.
But yeah,
oh, here we go.
There was Baum Inventions and also the shipper. Okay. Yeah, I had to answer that question on Twitter very often. And I was mainly inspired by Greg's approach to it. If you think about it, the NeoPixels. Okay, so spoiler, I'm not using NeoPixels. First thing out of the way. And that's because the NeoPixels use just to have them powered and not do anything with light. That take up 1 milliamp. That's like the roundabout house number that you're talking about. So on this thing, I have, I think it was 612. Yeah, it's 51 LEDs per PCB. So, so just having 612 LEDs on this tiny thing would mean that I have to have 612 milliamps sucked from the battery to just have the LEDs on there and not even have them on. So yeah, that was also Greg's kind of way to go at this. And also the NeoPixels, they are supposed to be very bright, and this little cube is, I don't know, it's you don't want it to be too bright because you want people to actually look at it and don't get any, I don't know, don't get blind, I guess. So you want to dial down all the PWM as much as you can. And if you're using NeoPixels from, I don't know, 0 to 16, you don't get a really good range of PWM values. And with the chip I'm using, this the chip itself has some brightness settings first, and then it also has a PWM setting for all the LEDs that are connected. So this gives you a way better range to address all the LEDs. And yeah, so I was kind of lucky there. I haven't tested it yet. I haven't calculated anything, but I'm pretty sure it's already doing way better than NeoPixels. And so when
the gauntlet has been thrown.
Yeah, if people like to see this with a NeoPixel, this would probably be easier to root also, because yeah, I basically, this is my first 4-layer board. Before that, I was always like, nah, I'm gonna root it somewhere, but still keep it in 2 layers. And this time I was like, oh no, I can't do it otherwise. So I really, this is such a complex thing to root, because you have, well, 51 LEDs, which means you have 204 connections to make that are kind of crossing or just swerving around each other. So yeah, that was pretty tricky, but in the end I managed to connect everything.
Except
and also yeah, except for one, but that was actually super easy to route. I was looking at it, I was like, click, click, done. And also the other bugs that I found, they were like super easy to fix. So the next version, yeah, it's multiplexing the LEDs, which you probably have to do.
But it's not your old school Charlie plexing, like 1000 LEDs.
Oh no. I think, I mean, Charlie plexing could have been easier. I'm not sure. I'm super used to do Charlie plexing matrices.
So all your old badges, check out Dave Darko's Tindy and so on.
Yeah,
all the badges are working with Charlie plexing, and everyone is stealing Dave Darko's design to design their badges, and maybe except for Tom.
Yeah,
the story of this one is quite similar to what Dave is saying. It was weeks spending on routing these individual LEDs. Crazy, huh?
Yeah.
Also the first 4-layer board, indeed.
Yeah, yeah, it's insane what kind of amount of time you can put in there just routing some LEDs, and you have more LEDs there. So yeah,
I think the problem is if you want to fill the entire surface of something with LEDs, now you're in trouble, right? If you have some space around it, there's a lot of things you can do. But if your entire board is covered in them, man, good luck routing.
And I didn't really test anything. I was just putting it together. I once found out that it's the easiest way to split the pentagon into 5 triangles that have the same angle and the same positioning. So there's a bit of an offset, but it kind of works out. And then I just was using this. I was just putting it into Inkscape, and then used a triangle. Was looking at it. Yeah, it kind of looks okay for 2x2 millimeter LEDs. There should be enough space in there. And when I had the Inkscape file done, I was making a footprint in KiCad and just imported it with the outline of the pentagon as well. So I already had the shape of the PCB and where I have to place the LEDs. And then I started putting everything together.
Wait, you placed the LEDs, or you designed the place for the LEDs inside of Inkscape for each one?
Yeah.
Wow.
Yeah. Because I didn't have any system how to get the coordinates out of it, so or just calculating the values for the triangles and stuff. So I just had the boxes for the LEDs, and then just drag and drop them there with a very small grid.
Could you also just copy the wiring of such a triangle and just rotate it by these, like, what is it, degrees in KiCad? So you don't have to route like every segment that's repeating, because that's already quite smart using the triangles and then just copying the stuff. And if you could just do the same with the wiring, you could basically save a lot of work.
Technically, yes. But
you would just tap into the on the backside, just tap in the like releasing star shaped like connections there or something. I don't know.
Yeah. Well, that's probably a good idea as well. I was just I had the LEDs connected differently in the first time when I was routing everything. So when I saw that I had them, I think I was looking at the triangles and was grouping the LEDs in like the first 3, then the next line of 3, then the 4 on the bottom. And I noticed that I grouped them by the common cathode, but it would make much more sense if they're common R, common G, common B, and then have the other ones go around there. I think I was looking at it for too long, and then at one point I was like, oh, okay, this makes more sense. It looks easier to route. So I was just going for that. I don't know what I did there in the end. But yeah, technically I was looking at them, and I have all the triangles connected in somewhat the same way, but I wasn't aware that you can even copy the section and put them in a different place in KiCad.
So what are the plans for your design in future? Will you like sell it, mass produce it? Will everyone get this?
No. This is something.
Can you put it on a Christmas tree, like an ornament, or?
Probably. So
jewelry, you can hang it on your ear or something like.
Well, the idea is to make it somehow portable. So the battery will fit in, and I'm going to put in the unexpected maker Tiny Pico, because it's very small and already has the battery stuff in there. And yeah, so somebody from the Hackspace was like, oh, I definitely want to have this. I have no idea what we're doing, but I want to do this because I want to have the cube. Or the
what's the BOM cost?
That's a good question. I think I have this prepared somewhere.
Just ballpark, like how many digits?
I never have it stored here because then I would feel very bad sometimes that I've spent so much money on a project and then just have it sitting somewhere. So yeah, but I do from time to time make some calculations in Google Docs. Oh God, I said Google. Now the chat is gonna. Anyway, yeah. So what? Oh yeah, I just wanted to say something about the simplicity of this. It's kind of easy enough to do it yourself. It's a bit tricky with the 04 or 2 capacitors and resistors, but there's enough space between them that you could solder them by hand because, well, I did. And so I think people can do this as well.
So you didn't
Not
use
everyone.
a stencil, or you just did it, started it by hand?
I have a stencil, but I didn't have enough solder paste, and I thought, okay, the main thing that I was able to, well, technically I only did the chip with the stencil or with the solder paste, and yeah, I regretted not using the stencil for those parts or for the chip, but the rest I had to touch up anyway, so I decided to just blob the chip footprint and then put the chip on it and use the heat gun on it, and that kind of worked, but it didn't connect the pins all the way, so I was standing there with flux and my soldering iron and went around the QFN chip, and that was a little bit of a pain. But yeah, it was much more trickier to connect the LEDs to each other, the ones that I had to fix. But this is fixed now, so people could technically use the PCB and just send it to LCSC. Or JLC PCB, and they have the RGB LED in there, and then you can get the board assembled, and that was not that expensive.
So is that on your GitHub, so the design files, or will you release at some point and announce on Twitter, or maybe?
Yeah, I think I might have put that on GitHub already, but people should definitely wait until I push my changes for the PCB. So
okay.
Yeah, I totally forgot to do that before the stream, but yeah.
Yeah, you were busy soldering by hand just to be finished with something presentable.
Yeah, just to have the
cast. Oh, thank you.
Just to have the half shell. But yeah, it was.
Dave, would you recommend people to have it assembled? How many hours do you think the whole thing would take to solder by hand?
I mean, it's you can't really hand solder this. I'm pretty sure you don't want to put your soldering iron on those tiny plastic LEDs for too long, and that's not really good to reach. So you definitely want to have this assembled. And I'm looking at my BOM right now, and it seems like the assembly was 25 euros. Okay, so the assembly was 25 euros. The stencil was 7 euros. The PCBs themselves were 36 euros. I kind of feel like I'm missing the LEDs. I think that's part of the assembly, though.
For how many pieces was this?
Yeah.
I've ordered 15 boards. So I have some other things in my assembly. I can maybe in my the parts list. So I've ordered 15 boards, and I totally spent. Okay, there are some capacitors in there. There's the IS31 chip in there. Some JST connectors. I've bought some cables from Adafruit that are the wrong ones, though. Sadly, it's like they had the quick connector on one side, and then they had like a 5-pin version of that. And I was like, I can't use this. Why did I buy this? So I just snipped off the 5 connection points, the connector on one side, and just soldered everything together. Anyways, I paid 180 euros for everything that I used in this so far. So.
Oh wow! Okay, yeah, but you have enough to make a few ones. No, how many?
No. Dodecahedron is.
Oh wow! Okay.
That's 12 boards, and I have 3 spares because I thought that might make sense to have 1 or 2 more than. But yeah, it's definitely one of those. It's not that much projects that turn out to be like 200 or 300 euros when you're finished with them.
Yeah.
So yeah, I definitely want to fix all of the PCBs and then maybe only have to order 10 the next time, so it's a bit cheaper. But in the end, yeah, I paid. That's 144 euros if you remove the other 3 that I have too many.
Okay. Oh wow.
Yeah,
Okay. Yeah. It's a lot of LEDs. Okay.
It is.
Anything else? Or I see David has a good connection now. Yeah. Oh, David maybe switched to his phone. Oh no, I feel bad. I feel bad. Let's switch over.
Oh yeah,
to
let's
David
switch over there
before his
data runs out.
rate is done. Oh, your sound
you should
is
unmute
off,
yourself.
Muted. You're muted.
All right. One of these days, I'm going to figure out technology. Yes, you guessed right. My 25-year-old ADSL out here in the middle of nowhere has finally decided that it doesn't enjoy my presence anymore. So I am now on my cell phone.
Oh,
no. But I do believe that my cell phone is a lot faster. So am I smooth? Are my hands moving correctly?
It's like way improved.
All right.
Yeah.
All right. So hopefully this will work. I'll just start over. So about a year and a half ago, I got totally obsessed with this idea of building a CPU or a processor from scratch because I was totally obsessed with Ben Eater's series of videos on YouTube. And he has this excellent collection of videos where he builds a processor called the SAP1, which stands for Simple as Possible. It's a little 8-bit processor, and he builds it on breadboards. So I was like, I want to build that, but I don't want to build that. You know, I want to kind of do my own thing, right? I want to learn. I want to learn about this without just copying somebody else's work. So I said, why don't I build that out of vacuum tubes? There's just a very real reason why vacuum tube computers are the size of buildings, and I don't have the budget to do that. I have a budget of like $4.50. So I had to figure out a different way to build a processor out of vacuum tubes that stayed within my budget. And the solution was to look at processor designs that were smaller or simpler. So I'm going to try and share my screen here again, only I'm going to do it through...
Okay, through me?
Yeah, through... We'll do the entire screen here. We'll see there. Can we get that up there?
Yes.
All right.
There you go.
So can you guys see this picture now?
Yes.
Yes.
All right. Awesome. Okay. So in the late 1970s, Motorola designed a chip called the MC14500. It was a 1-bit microprocessor that was designed to replace relay ladder logic in industrial environments, most notably like traffic lights. Traffic lights are incredibly complicated things. So they came up with this design to do that. So you'll notice right up here at the top, it says data. This is the 1-bit data bus. Like when we talk about modern CPUs, we say, oh, it's a 32-bit CPU, it's a 64-bit CPU. We're talking about the width of the data bus. And so in this one, it is 1 bit wide as opposed to 32 or 40, 64 bits wide. Now, I really like this design because it seemed like something that I could tackle with vacuum tubes, but I didn't like that it only had a logic unit in it. So this on the left is the list of instructions that the Motorola chip can do. And so the logic instructions are pretty much from instruction number 1 here all the way up to instruction number 7. It's got load complement, and, or, exclusive, nor, and some other interesting complement ones there. But there's no addition or subtraction. So sticking within the confines of those 7 or 8 instructions that I had there, I kind of came up with this idea here on the right. I wanted to do addition. I wanted to do subtraction. I would need to force a 1 into the result register. I wanted to do NAND or an exclusive OR, because if I did inverse of those, that could get me AND, NOR, or exclusive NOR. Other than that, the instructions are all the same. So I came up with this design, which is pretty much identical to the Motorola chip that we were just looking at. Still has that 1-bit data bus right along the top. We have input enable, output enable to control input coming into the system and output leaving the system, and this write pin here is quite important for writing to memory. But it has now a full arithmetic logic unit with a carry register and a result register that we can work with from there. And the really interesting thing about the processor is that there's no memory on it and there's no program control. Because it was designed to be used in industrial settings, they didn't know what kind of memory was going to be available or what kind of program control was going to be available, which gave me some flexibility. But I haven't gotten as far as building these other three things: memory, program control, and input and output. I've just been working on the processor here. So it's important to keep in mind that when I show the collection of tubes, there is no memory, there is no program control. The memory and program control is still the human me. And so this, I just thought was kind of a fun picture. This is the logic level design of what we're about to look at. So we can go ahead and stop sharing my screen now.
Okay.
All right, so we will rotate the camera here. And this is the entire processor. Again, just to reiterate, there's no memory on this and there's no program control. So I have to do that. So I also made a little remote control here. Now I'll go ahead and turn it on. This is my power supply here. I think my power supply weighs more than everybody's projects combined. So I'll turn it on. It's gonna spike up to about 15 amps, and then it'll come down, and then it'll have another spike as the relays kick on. And an important thing to note here is that everybody thinks vacuum tubes have to run on super high voltages, but this is 190 vacuum tubes. They're almost all identical. They're all the 6AU6, and I'm only using 24 volts and negative 12 volts. So at any point in time, at the most, there's only a potential of 36 volts on here. So I can lick my finger and just touch anywhere in here, and there's no danger there. Because I'm an idiot and I do stuff like that. And so if there was like 300 volts or 500 volts or whatever people often run vacuum tubes at, that could be quite dangerous. But this is like super, super safe. So if you see me pointing at stuff, or if you look at that and you go, oh, there's a bunch of exposed wires on the PCBs, like it's okay. It's super low voltage. And I can get away with that because I'm not doing any power. I don't need any power. It's just logic signals going back and forth. I just need logic high or logic low, and I just need that to be an input to another logic gate. And vacuum tubes are super high impedance, so it works really well. If I had to drive like a speaker or something, it falls on its face. But it works great for this. And I have some VFDs here that are going to be my display. We'll see if I can get the thing to reflect light. The most important ones are going to be these three here on the top left. This is going to be the data bus. So whatever's sitting on the data bus will illuminate there. Right now it's nothing, but if I flip this switch, you can see it turned on. So now there's a 1 being forced onto the data bus. The one in the middle is going to be whatever's in the result register. That's a result from whatever operation we just did. And the one on the right is the write pin, like WRITE, write as in I'm writing to memory. So whenever that pin goes high, whatever's on the data bus gets stored in some address of memory. Now the tube processor has warmed up. I'm just stalling to give the tube's time to warm up. So it's warmed up, so I need to initialize it. And the first thing I'm going to do is I'm going to do an instruction of 1010. I'm going to force a 1 into that. That's going to turn my input enable register on, so I can bring input into the system. And then I'm going to turn 1011. That's going to turn my output enable register on, so I can take output out of the system. And then I want to make sure that result register and carry are at 0, so we'll load a 0 into the result register, and then we'll add a 0 to that. And then we'll do 1. There we go. All right, so now the system is totally initialized. And so like what can it do? So let's add two numbers together. We're going to add the numbers 5 and the numbers 6 together. This is like super rudimentary stuff. 5 plus 6 is 11 or 12, depending on what school you went to.
Spoiler alert.
Yeah, spoiler alert. So 5 in binary is 101. 6 in binary is 110. And so since it's a 1-bit processor, we have to do it 1 bit at a time. So we'll start by loading the operand, the first bit of the first operand into the result register. So a load operation is 0001. And the first number is 5, which is 101. So we'll set our data to 1. We'll load that into the result register, which it didn't do, of course. There we go. Yeah, all right. I don't know. I had to make sure an indication was on. Okay, so we've got a 1 in the result register now, and we want to add that with 0. So we'll turn that off, turn U on, add it to 0, and then we want to output that. So output is going to be operation of 1000, and when I push and hold the clock, we'll see if you can see that there. The right pin is illuminated and the data bus is also illuminated. So this one and this one are on. That means that the data bus is outputting the result of the addition of our first 2 bits from our 2 operands. And that is 1, and that's going onto the data bus. And our answer that we're looking for is 1011. So that's correct. We've got our first bit out, right? So if we do the next bit,
so the carry, 1 second, the carry is still held in the processor then?
Yeah, so it's a little weird to be able to actually point to parts of the processor. But right here are our 2 registers. This register on the bottom here is the result register. So this is holding the result of the addition of the 2 bits. But if there is a carry, that's stored in this register right above it, these 8 tubes right here. Yeah. So this is the carry register. And then that's fed back into the arithmetic logic unit. And the arithmetic logic unit is this collection of 16 tubes right here. And these 6 over here that are just hanging out for fun. So this kind of strip right here is the collection of the arithmetic logic unit, the result register to store our result, and the carry register. So our carry is stored right here, right now. We've done the first bit. We'll load in the second bit, which is 0, and then we'll do an addition with the second operand, which is 1. That stores a 1 in the result register. We'll output that onto the data bus. And then there we go. We're outputting the second bit of our addition onto the data bus to store, which is a 1, which is correct. So if we do the last addition, we'll load a 1 into there. We'll add it with a 1. And then we'll output that onto the data bus. We can see our right pin went high. I don't know if you can see that. Our right pin went high, but our data bus is low. So we're outputting a 0 onto the data bus. That is the 3rd bit of our addition. So we've got 011, which is correct so far, but we need to get the carry bit into memory now for our final answer, right? Because we added 2 3-bit numbers together, but our answer is 4 bits. And so the carry I can actually physically see from an indicator that I have on here is storing a 1, but I need to get that into the result register and then output it.
So you add just 0 and 0 and you get the carry.
Exactly. So he's nailing it. So I load a 0 into the result register. I add that with a 0. That brings the carry into the result register. We output that onto the data bus. That's a 1. We just did 5 plus 6 to give us the answer of 11, and we did it with 190 vacuum tubes.
Oh wow, that's awesome!
That's incredible.
Yeah.
So that's my vacuum tube computer. I'll kind of angle it here, so you can get an idea of the sense of scale. If I sit next to it, it's not small. Like, it's very, very large. To kind of, let's see if I can get the camera far enough back here to talk about what's going on. Whenever I flip these 4 switches here, I'm setting up an instruction, and it uses a 4-bit instruction. So that 4-bit instruction comes in through my kind of ghetto harness here, and it comes all the way up to the top here into the instruction register. So each collection of 6 tubes here is a D flip-flop. So it stores the 4 bits right there. So that's my 4-bit instruction. And then it decodes it. That's what this collection of tubes here is decoding it and then buffering it. And so that takes that 4-bit instruction, decodes it into 16 control signals, and then buffers each of those control signals. And then you can see, like, down the bottom right, or down the right side here, all the way to the bottom, is what looks like a huge bus. And that's pretty much the 16 control signals coming down the right and then spearing off to whatever parts of the processor that need to go to. This section along here is just like some glue logic plus an exclusive OR gate so that we can do subtraction by doing, I think, 2's complement. And then below that, we have the arithmetic logic unit and the result register. And then along the bottom, it's a little hard to see because I got power supply and stuff in the way, is our control for outputting data. So if we want to put data onto the data bus. And one really unique thing about this is that it does, because Motorola didn't know what kind of like memory or program control or any of that stuff was going to be set up. They didn't know like if they would have the ability to jump to a different location on the program counter. So instead of saying, hey, we want to jump to a different location, they just set up a generic flag that says, if you want to do that, you can handle it on your own. Or you can use our built-in solution, which is the output enable. And what this does is it turns that right pin on or off. So whenever I was hitting the clock and the right pin was coming on, we were storing what was on the data bus. But if I do like a conditional thing that says, hey, turn the output enable register off based on this value, we can turn that off. Now the program counter still goes through and executes all the code, but nothing can get out because the output enable register has stopped it. And then you can force that on later in the program. So you can set up a program as like a really long loop, and then you can have a conditional statement in the middle. And it still executes those instructions, but because the output enable register is off during that conditional, it doesn't output anything to memory, and you don't save anything from it. So that's what's going on the bottom half down here. So in the future, hopefully for 2022, my goals for 2022 are to get some RAM going. Now, RAM is difficult. A lot of people have had some like excellent suggestions and ideas about how to tackle RAM. The hard part is addressing it. So until you get to like very large RAM sizes, stuff like core memory or delay line memory or stuff like that doesn't really make sense because I still have to address it 1 bit at a time, which is just intensive. And so if you think that this is a lot of vacuum tubes, the memory is going to be about 270 vacuum tubes as I have it designed up here and on the computer now. And then program control, my goal for that is to use reel-to-reel audio tape. So that way I can write a program on the computer, save it as an audio file, and then play it back. And then the program control board itself will read that audio file, decode it into a collection of bits. I'm probably going to have about a 12-bit instruction word, and then execute it from there. So that's kind of the overall goal of it. And then big, major, like long-term goals are to ultimately have an input-output that will output either 5-bit Baudot code or 7-bit ASCII. So that way I can have this thing send hello world to a teletype or to anything that has RS-232. So the total ultimate big goals of this entire machine is to be able to calculate the Fibonacci sequence and to be able to print out hello world. I figure if it can do those two things, then it's a fairly capable machine. But it's going to be big. Each, this board, the backboard that it's on here is 1 meter by 0.7 meters. And each section of the computer is going to fit on the same size board. So there's going to be 4 of these that are this size. So I got to build a rack for it. It's going to be 2 meters tall by 1.5 meters wide. And it's going to use a colossal amount of power. As it's sitting here right now, the 24 volt supply is pulling 11 amps and the 12 volt supply is pulling 6 amps to give you guys an idea of the level of power draw that it has. So yeah, there we go. All right. That's my vacuum tube computer processor thing.
Wow.
Awesome. It's awesome.
Pile of stuff rightfully says in the chat that Ian is not the only mad scientist in this stream, and I wholeheartedly agree.
So how long did you work on that? I can remember the last time we have been on the MakerCast. You showed like the 555 timer, I think.
Yeah.
And it was like just in the planning phase, or you just started working at it? How long is it ago? So how long did you take for that? Because it seems for me that like I take like ages to do the simplest projects, and you come up with a complete computer, vacuum tube computer, in like a super short time.
It wasn't super short. Like to get this was about I think just about a year, about 1 year long.
Okay.
There was a lot of like planning and figuring stuff out. Like there's a ton of documentation out there on using vacuum tubes, both mostly for audio stuff, but there's a lot of really good information out there from IBM about using vacuum tubes for computers, but none of it applies to using vacuum tubes at low voltages. So I had to do like a lot of testing on my own of like what tube was good, what tube I could afford, what tubes worked well at the voltages that I wanted to work at, how I should set that up, like what resistor values I should use. Should I use a bigger plate resistor? Well, if I use a bigger plate resistor, then my voltage divider resistor on the input has to get exponentially larger. Then there's, fan out issues, like with CMOS chips, like you don't really have a fan out problem. And even with like a good MOSFET, like a fan out problem is like you can have the output out of one MOSFET feed the input to like 100 other MOSFETs, right? But like one logic element on here, whether it's a NOR gate or a NAND gate or even an inverter, the output of that can only feed about 3 or 4 other inputs before I run into fan out problems. So then I have to work in how to, where can I stuff a buffer in there? So I build a cathode follower buffer. And a cathode follower buffer lets me get that fan out up to about like 15 tubes ish. I don't know. I haven't really pushed it that far yet. But now, okay, so I've got these 16 things. I've got these, these 16 control lines. They've got to go to a bunch of places. So now I got to stuff 16 cathode follower buffers in there somewhere, which is what, this is right here. These 16 tubes are all just cathode follower buffers to fight the fan out issue. So there was a lot of headaches about that. Also, all of the PC boards here are all made at home on my extremely oversized Bridgeport EasyTrack 3-axis CNC mill. So I design them up on the computer, I turn them into G-code, and then I go out and cut them. And a board about this size, so this collection of 8 vacuum tubes right here, this board probably takes about 3 hours to cut. So like, I set up the mill, I get it installed on there, I start the cut, I come back inside and play video games for an hour and a half, and then I go out and I babysit it while it does drilling and it does the outline cutting and stuff like that. And then it takes probably another 2 hours to 2.5 hours to solder that board up. So it's an extremely time-intensive project, but because of COVID and the world in general, I had a lot of spare time.
Okay, cool.
Yeah.
Great. And your supply of tubes is still like up, or is there like any end in? So do you have like to save some tubes, or do you have like an infinite supply somewhere?
So the vacuum tubes are tough because like the number one thing that everybody tells me is like you should have built it out of dual triodes. So I'm using pentodes. So like a pentode is just like, imagine a fancy JFET stuck inside of a glass tube, and a dual triode would be like 2 JFETs stuck inside of a glass tube. So obviously it would make sense to use dual triodes versus pentodes because I get twice as many logic elements out of a single glass tube. Except that most dual triodes are very popular among the audiophile guys. And so like a just run-of-the-mill dual triode can run anywhere from $1.50 to $2 a tube, all the way up to $100 a tube. You kind of get your whole run of the gamut. So like the unwanted, unloved dual triodes, you can maybe find for $2 a tube. And so I was like, it's got to get cheaper than that. Like I can't afford to do 600 vacuum tubes at $2 a tube, right? So the pentodes, these are all 6AU6s. And 6AU6s were an incredibly popular tube back in the like 50s for use in like TVs, for use in electronics equipment, pretty much anything except for audio tubes. And they even used them in some audio applications as like a preamplifier tube. But they made them in just like droves, millions of them. So there's a lot of them out there that are called pulls, where people just like rip them out of something, they don't test them. And so I've just been like keeping an eye on eBay. And if I see a collection of 6AU6s pop up for less than 80 cents a tube, I buy that collection. And so I think currently I have around 1,200 6AU6s in the collection.
Oh, wow, cool.
So I have enough to make it to the end of this project, and then some. I'm thinking that by the end of this project, I'll use probably around 600 vacuum tubes.
Oh, wow, cool. So, yeah, are you releasing the designs or design files, or?
Yeah, if anybody wants them, they can hit me up on Twitter or Facebook or Discord or anywhere, and I'm more than happy to supply them to you. Now, there's some caveats with that because it looks like I've just stuck the vacuum tubes directly into the PC board here, but I'm actually using these little 1mm PCB pin headers that I found a bunch of. So, if a tube goes bad, I can pull it out and put a different tube in. Okay. But because of that, I have to have a custom footprint on the PC board itself that doesn't match anything except for my specific way of constructing it. But if anybody wants, the Gerber files, if anybody wants the logic diagram, it's all available. It's all free. Just ask me. If you can't find it, just ask me, and I'll be happy to send it to you.
Okay, cool. Thanks, David. That was an awesome presentation. We are almost like 2 hours already, and I still have to present. And I even forgot to introduce myself. I don't know. Oops, let me shift me around. I'm just hiding behind a duck now all the time.
It's your channel, so people might know who you are.
Yeah. So most probably people know me already. If you are visiting from like cross-linking on Twitter and so on, announcements. I'm also a YouTube maker almost like full-time, and I wanted to prepare some stuff to show today, but unfortunately I'm always unprepared, like on my streams on Wednesdays. So I have here like this acoustic levitator. That's like, this design is like really old. That has been around on YouTube's already, like, and on the interwebs ages. And I just wanted to hook this up and show it, because I started to playing with the ultrasonic transducers. This like distance meters. They are like really cheap. You can get them for $1 or something, or $2 on eBay right now. And it didn't work. So I have to maybe share a video or something. Let me check. Can I share a screen? So I can share that one. Oh yeah, that's not that yet. So here, I have a video for you as well. So I'm on my trash channel. That's like a different channel. I might link it in the description, or you just search for bitluni's trash. I'm doing like the one-day projects on Wednesday evenings, European time, and we basically like did this basic levitator, and we can maybe I do it without the sound, and here you can see. That's quite easy. It uses only like this this amplifier board here that you can easily get. And what I initially, this is like just a mini side project. And what I was thinking to do is to stop that. It's distracting me. To design like phased array. So it sounds really like complicated. And I'm preparing a video on that to maybe explain it easier. So what it basically does, this is like one design that I'm finished with right now. This is like, should be only a test, because it has like not only these ones here have like a transmitter, and this is T transmitter, and a receiver. So this one this one, the transmitter, generates a 40 or resonates at 40 kilohertz, so it's not audible for human, maybe for some animals, most probably. And this one receives at 40 kilohertz. So basically, it generates a pulse. You can generate a pulse with that. That pulse will bounce off obstacle and return. And basically, the delay calculated, like you can use the speed of sound to calculate the distance to the object. And my thought is, okay, if we put like multiple transmitters, these are only transmitters. So we have 8 transmitters, so we can maybe control with one register of a microcontroller. If we put them like really close together, these are like 10 millimeter transmitters close together. And if we time the pulse of each individual transmitter precisely, we can create an interference pattern that basically creates like a very sharp ray. This ray of sound, you can even change the direction if you change the timing. I can maybe show that on this emulator this was like, okay, ignore all that other stuff, but what this was like the initial thing. And you can see this is like the phase. So if you think like you have like the sound is like a sine wave, and a complete sine wave, like this is like the phase of 1. So because it's between 0 and 1, or usually like 0 and 2 pi, but I call it just 1 to have it. I can basically shift for one transducer for shift this phase back and forth, and the pattern changes here. This is the simulation, and you can control this precisely. If I like, this is the amplitude. If I just if I have only one transmitter, you get like, this is the cone that I get from this transmitter. Maybe not like that wide, because there is a slight fall off that I calculated. I have like in the data sheets there are some data on the fall off with the angle, and I just designed some here so we can see it. So if we use that one, we can basically determine there is something in front of us, but not really precisely. But if we take like turn everything on again.
So bitluni, this image, is it a side view we're looking at?
Top view. So we have the transmitters. Transmitters are down there, and we have the array like next to each other here, and we looking at the top, and this is the sound that's moving away from the transmitter. So, and we have like up to 8 in this simulation. And basically, we get an interference pattern. The more transmitters we add, we get an interference pattern. This is like a little bit off, but I have like this slider, which basically like delays. You can see that you have like a linear delay between the individual transducers. And what we can do at the end is, by changing this delay, we can generate one ray like this one here, and sweep, like do a sweep scan in front of us. So actually we can use this already to maybe have a distance map in front of us, just by using an array of multiple ones than just like one transmitter. So I designed that one with some I have like found cool drivers to not have many pins and many components. I used basically like stepper drivers, which have the full bridges inside of them, and I'm using like a push-pull configuration. So I'm just flipping the polarity plus minus around, and this is basically indicated with a 0 or 1 at the logic pins here. So I can easily connect this with few pins to microcontroller, and I have only like 1 or 2 enable pins, one standby and enable pin, so I can turn it completely off. And if it's not turned off, it basically sends out the signals in some way.
I have a question.
Yeah, sure.
So what's the distance between those high peaks?
You mean here? It's
Yeah.
for 40 kilohertz, you have the speed of sound. It's, I think, 8.5 aroundish millimeters. So 8.5 millimeters is the wavelength of 40 kilohertz in air, like in room temperature. This can be precisely calculated, but I'm assuming always like 20 degrees C. So I'm not really like doing any sophisticated stuff. And so I have also like this distance. I can simulate like the distance of the transducers, and you can see when I pull them apart, so this is like 37 millimeters, it's like the pattern falls apart. So I just by writing this simulation first, I found out without any reading, because I'm lazy, I found out, okay, the closer I put them together to match like this the wavelength, the better we get like a ray out of that. So a perfect ray with like this ray and this one that comes sideways would be 90 degrees if we have like 8.5 millimeters separation between the transducers. But the smallest ones that I found here that you can solder by hand and not be like in like a scanning head of like an ultrasonic medical device. These are 10 millimeters. So I put them just 10 millimeters apart. And now I can control like using this phase shift, I can control like the angle of this ray. And I wanted to verify, okay, is this doing what it's doing? Because I can see that. And there was a video of Charles Lohr where he used the CNC to map the Wi-Fi signal at his home and show it. And I thought, okay, well, I can maybe switch. I can still share it, but I will switch my camera. I hope I can switch my camera. Oh no, here's like, wait a second. My cam here. So I got my pick and place machine that I currently not using because I don't like make many boards anymore. And I thought, okay, let's use that to put like on. I have. Oops. Sorry. I will move it around. Can I? I need to switch the layout here, I think. Okay. So I like zip tied the transmitter, so the receiver part on the head of the CNC mill. And on the right side, you can maybe see on like the axis, there's the array. You can maybe get up and show it here. Here is the array. And on the head, we can see the receiver. So I thought, okay, like let's control that using the control the CNC with G codes over serial. That's easily possible, like with your 3D printer. And there is like on the head, like the receiver is just an Arduino Nano that takes like the signal and with an analog read. That's another serial, and my array is also just connected to an ESP32 that receives like over serial the command of the phase shift. And what my screen share does, let me switch to the screen share here. Oh yeah, what my screen share does here. Okay, it shows a web page. So this is HTML with web serial. So this is all like completely in JavaScript, this whole simulation, and this is basically like a canvas and so on. And what we can see here, this is already the output of the CNC. So I can home my CNC. It will find like the 0 point, and this is the receiver. This is the signal that I received there. and this is my array. And whenever I change like here the phase, I will get an OK from the array if it's working. And then I have like implemented, this is like the feed rate. I can basically run a scan right now. So the CNC will just go like in snake movement and will basically map out the complete space here. That will take maybe a few seconds. There's one problem left. This receiving the signal on the receiver is like is a little bit delayed because I perform like a real-time integration on that signal. So we have a slight shift here from row to row because I'm going from left to right and so on. But you will basically, you can maybe make out the pattern at the end. It will more or less match with what I calculated there. We are still not in the range really. So this is like, I'm just too far away, but we will start to see a signal coming here. Yeah, and while we are doing, I can switch. Okay. We don't need to see. Okay, here we go.
Oh, you're doing that live.
Yeah, I'm like, doing it live.
Fast forward, fast forward.
No. Yeah, I'm doing that's why I'm using this high feed rate. Usually I can run it way slower, but you can already maybe see, okay, we getting this signal like it will appear like we got it here like that. So I can keep it running. But basically, yeah, it looks like I'm going down the rabbit hole, and I won't do more. Like, there is like on Hackaday SuperCon, I think it was 2018. There was a team that showed already like the phased arrays, and they had like on their research group, they used like big 2D arrays to do this levitation that I was showing. Like in 2D, in space, they can move things around there. And this is basically also like one use case, one goal that I want to do. Okay, oh, here you can see there is like a dip in the, so there is like a cancellation of the signal that we get. And what I assume is basically, there is a reflection of the table that I'm sending, like, of the CNC bed or the beam where the head is mounted. So I assume there is basically this cancellation pattern also because it bounces off the table or something. So the ray just continues, and this one array won't be visible because I think the attenuation in the angle is higher than I'm simulating, but this one is already visible. So yeah, that's what I'm working right now on.
I have two questions.
Okay, yeah.
And maybe we'll start with a nerdier one. Would it make sense to drop the frequency so you have the same amount of distance between the the sending, the emitters? Yeah, I was just calculating it in an online converter, and you might want to go to a frequency of 34,000 or something like that. But then again, is it even possible for the emitters to go to a frequency like that?
Yeah, they can. You can even go. So when I was my first test that I did is if I get anything out of my like ICs here, I wouldn't do it like that here with measuring. So I just started sending out like 8 kilohertz, so I can still hear it. But the resonant frequency is like, or like the peak. Maybe I can pull out the data sheet. If you just take a look at the data sheet, there is like they are not very powerful at those frequencies. So I could go lower, but then it's already audible, and it will be like very annoying.
Well, 35,000 wouldn't be.
Yeah, I can.
That
I can. We can even. Okay, let's try. What's the perfect frequency you say?
Well, if it's based
10
on 20
millimeters?
degrees and speed of sound of 343, then it's 34,300. 34300.
Okay, so this will be the simulation of that. So that would be more of a matching frequency. It's not a huge difference, but it would like make like around 20 dBs or something. So I get a lot more power out of my transducers if I use like, it's not perfect 40 kilohertz. I think the perfect frequency is almost 40 kilohertz. So between 39 and 40 kilohertz. But yeah, I have also the simulation for that. And the lower you go, the better it gets here. So this one looks really like clean, yeah. But this is 20. This is already audible, so
yeah.
I tried for that, but yeah.
So did the line get thinner when we went to 35,000?
No, I don't think so. I think you get fewer like fewer of those effects here. So if we change the distance, we see more and more of additional lines appear. So we just get a cleaner signal, but I don't think it, because of like the wavelength, I think it gets a little bit wider again. So if we go like 30K, I think it's the same, 34. Yeah, it might be more optimal. So yeah, we have a try, and we can change this. It's all in software. So.
That's cool. So
yeah,
what's your I don't know, that's maybe a bold question, but what's your end goal for this? Like, do you want to move certain things around in 2D, 3D, 4D? What's your goal?
Okay, so my next thing, first of all, I want to do like this sweep distance measuring. This is like very easy. I can do that, and maybe the video that because I have enough material already for like a release, I would just show that I can actually use it for something. I have already a use case to measure a distance to maybe map some obstacles in front of me, and this is like the first use case. The second, if I put like on that one here, if I put like two arrays opposing each other, so I have enough pins on the ESP32 to control like the 16 transducers simultaneously, and each of them like with own frequency, own phase shift, whatever, real time. So on the ESP32, I will basically try to put them like that, and maybe move like particles like in 2D in this plane basically around. So this will be, if that works already, I'm very satisfied. But I already have like, maybe can I show it? Okay, I already like, I'm planning a hex design, and I'm starting with a board of, I think it's 30 and 61 transducers, because they are not very cheap. If you buy them like of one transducer of Mauser, you pay €3. And if you buy them of Alibaba, you can maybe get them for 20 cents dollar. So a little bit cheaper. And I got, yeah, of course, please don't go to LCSC and buy them off. I might need more. So I got them off LCSC. They are, I think, 40 cents each. So I bought 100, I think. Are these 100? Yeah, 100 pieces already. So I paid, I think, with shipping $50 something, $50-$60 already to solder it up. So I don't need to get them off Mauser right now. But these came like precious parts. I used Eisler because they are sponsoring me, and I got them like of my store credit. Yeah, and that's the ultimate goal would be to have like 2D hex arrays, and I think, I don't know, I won't make it a product. I think I can see if it's possible, but parts shortage is like an ass right now, so I don't even try. Oh yeah, I think that's all from me.
What's the like maximum distance that you can get out of it? It was a little hard to see on your pick and place, but it looked like it was like I don't know, like maybe 30 centimeters maximum distance or something like that.
Oh no, I think this is oh yeah, wait, this is 55 centimeters, so this will be maybe 30, but I assume the ray can go further. We can so I'm running them currently at only 10 volts. So push-pull, it will be 20 volts right now. I can go higher with the power. I can crank it up. We can maybe cancel like the phase shift, so we get a ray, like straight ray here. Okay, this and rerun it. I can basically. Oh, you can see my screen. Okay, where's my screen? Okay, here's the screen. I could crank it up and rerun it. And I think usually you can, if you are scanning for like obstacles, I will turn on the power, like crank it up. It might die. I don't know. I will set it to 12, just increase the power a little bit. But they will heat up from at some point. The transducers will heat up. At 10 volts, I can run them like infinitely. That won't harm them. So let me rerun that scan. Maybe we will even start seeing somewhere here, but it could be that we have already like this cancellation pattern, or we have still a cone, and we have like the table and so on. So if we would measure it in free space, it might even show up further away. Usually you can measure up to 8 meters. If you're scanning like distances. So we can already see a speckle here. I think we will find out. I don't know. We will try. If you want to move stuff around, so with this levitation, you can't go very far. So you would like need to have like a really high voltage or something, but then they will melt at some point. So here we can see that's maybe half a meter. Not here. This one will be half a meter, maybe 40 centimeters. We can see like this ray already. Okay, I will just stop it. This is quite annoying. Let me stop it. Stop it. Oh, I'm pushing the wrong screen here. Okay.
Don't forget to dial down the voltage again.
Oh yeah. I don't want them to melt. I will just unplug it.
Yeah, it's a situation like, oh, live stream. Yeah, let's talk about other stuff melt. For half an hour now.
I have spare ones, but
well, shortage. Do you really have spare ones?
Oh man.
Yeah.
I at least have enough to make a recording. Okay, yeah, we are already over 2 hours in. I didn't prepare a quiz. Usually it would be common to have a quiz. I'm sorry about that. I wanted to do a quiz about like 2021. So like with numbers, but the numbers are not out there. So like how many rockets launched? Okay, that one number we have, but like how many electric cars were sold 21 and so on. But
I don't care about cars.
You don't care? LEDs, how many LEDs were produced?
That's a good, interesting question, yeah. I need more pink blinking, slow fading LEDs.
Yeah. So instead of a quiz, we might like, so what are your plans for 22? What do you want to achieve? So we heard some some plans already, like by David? Anyone wants to share?
I have this bunch of wires that I'm hoping to turn into a project. I can quickly show it.
Oh yeah, sure.
So there's this thing.
Let me share you.
There you go. So this, in the end, will be a device that you connect to your computer via USB.
Yeah.
And it will present very many speakers and microphones to your system. You can send applications to a microphone. With these faders, you can mix them together, and it will send it back as a speaker, or rather the other way around. So applications send to speakers, and device sends back via microphone.
Oh, that's cool. So you have an analog like mixer.
Yeah, so a hardware-based mixer. So you know, if you're a streamer, you want to be able to play sounds like this. And currently, I'm running this in software. It's quite a setup to do. On Mac, you have Blackhole. On Windows, you have a virtual audio cable, I think. You have to set up this whole system to reroute audio signals and these kinds of things. It's a bit buggy. And so I wanted to see if it could be done nicely also in hardware. So there's commercial products that already do this. TC Helicon makes this thing called the Go XLR. It's a really fancy device like this, but it sells for 500 euros. And even the smaller version of it, I think, is 200 or so. Yeah. And so I figured, how hard could it be? And I discovered during this past year that both audio and USB are really hard. So my hope for 2022 is that I'll be able to finish and have an open source hackable version of this thing.
Okay, cool.
I hope it's not offending to ask, but how much did you invest in hardware already in your
So
prototype?
this is an interesting point. So currently I have one prototype and I spent, I think, around 1,000 euros. So I could have bought two of the fancy ones, but there is a reason for it, right? So because of the chip shortage, almost any interesting microcontroller that you would want to buy is unavailable and will be unavailable for years maybe to come still. And so I bought the last 100 pieces of a fancy NXP chip, the IMX RT1024. Last 100 pieces globally, worldwide, that I could find. Just had them, shipped them over. I didn't care how much it cost. Just so that if the project succeeds and I make the one device that I personally want to use, there's also a bit of stock for anyone else who might want to have one. So I can do a very small production run of it and share it with some acquaintances. So that's the reason why it's now super expensive. The parts for the prototype by themselves were not too much.
Okay. Yeah. Very nice. I think it's my turn, right? I'm asking the offending questions.
David just unmuted himself. David?
Well, I was thinking if we're talking about interesting stuff that we've been building aside from the main project that we showed, I've got an extra project that I haven't told anybody about, but I made a video about that goes live tomorrow. But I thought I would spoil it here if you guys wanted to see the spoiler.
Yeah.
So
yes, I want to see the spoiler.
So we'll tilt it down here a bit. We'll see. There we go. So you can see there's a bunch of knobs and 4 vacuum tubes. I'll turn it on. And as these warm up, I'll tell you what it is. This is a vacuum tube Atari Punk console, which is like the first foray that anybody... Oh, there we go. I don't know. Can you guys hear that? Is it annoying?
Yeah.
Yes.
Bar generator.
Sounds like something that's slowly dying.
Yeah. So one of the things that I really wanted to do more of in 2022, since we're talking about 2022, is I want to do more audio stuff. I'm deaf in one ear, so audio stuff to me is kind of not a great avenue to go down. But I find the circuit designs and the way to build audio stuff with vacuum tubes to be really fascinating. And so one of the first things that I wanted to try was to build an Atari Punk console. Now I have the 555 timer that I've been working on, and I talk about it in the upcoming video as well. And it's made some pretty good progress, although there's still like 6 bodge wires on the back. So, you know, time for the next revision of boards on that. But the Atari Punk console is built by putting 2 555 timers together. And I did that, and it was really exciting, but I was like, I can do better than that. I can do an A-stable and a monostable multi-vibrator out of just a few tubes. And so this uses 4 6DJ8 dual triodes. But the 6DJ8 dual triode is like a 6-volt tube. And dual triodes all have like a nearly identical pinout. So you can rip these out and you can put in anything else that shares that pinout. It's like 6 CG7s, 6 FQ7s. I tested a couple of 6N1Ps, a Russian tube, 6 BZ7. I tested a bunch of different ones, and they all have like wildly different sounds. And you can't test like a Texas Instruments made 555 versus like a Philips made 555 and get a different sound. So that's something that I thought was really cool. This actually runs just on a single 24-volt wall wart, which I also thought was quite fun. So it's not high voltage. Again, I can like touch anything and not shock myself. So that's my my plans for 2022 is to do more audio synthesizer fun stuff like that.
That's cool.
Nice.
It's like a cartridge, so that you get a sound font cartridge.
Yeah,
like a YouTube is a new cartridge.
This may be because I got pinged for copyright in some music, so maybe I should make my own synth music or something.
Okay, cool. So people, don't forget to go to David's channel and subscribe to get the newest updates. Okay, Dave, Darko, you wanted to share something?
Yeah, sure. I just wanted to say that I really enjoyed the chat right now with all the audio files gone along with comments. Oh, let me just slip. Anyways, so I still have this project going, and I have to work on this. Or it goes like this. It's the smartwatch, the calculator watch that I found, where I replaced the PCB inside, and there's an LCD controller chip on there, or basically a SAMD21 plus LCD controller within one chip, the SAML22. I have no idea how to program ARM stuff, and it's really hard for me to get a blink going. And I definitely have to look up the GNU CCC compiler thing, how to get stuff going. I managed to upload the firmware that someone else made for a different smartwatch replacement board. But yeah, I have lots to learn there. So this is probably my 2022 project. And then also, just get my music setup going again. I'm using this huge cork thing as a display holder for the LED board there. This feels so wrong. And I just want to have a setup where I can just turn on anything and then just play it and maybe record it. And that's why I got this as well, because you can record with this. And it was a bit expensive, of course, but this thing is out there for 10 years and they're still putting out software updates, and I was recently updating it, and it's now working as a USB sound card as well, if I got that right. But just play with some music. And then I also, when I was in America, got myself an Oscitone Scout, and that's an Arduino based little synthesizer squeaking thingy, which sounds a bit better than the 555 timer based keyboards. And someone published a port of the Mozzi oscillator Arduino thingy for this guy, and I can do some pretty neat sounds now. And this is something I still have to build up, but I can totally recommend get a kit, or maybe order the boards for yourself and put all the parts on, and then program it and print the parts yourself. this is also acceptable to do. And yeah.
Cool. So it sounds
really
like
nice
22 will be about audio a little bit.
Yeah.
Ian.
Yeah. So besides the projects I mentioned, the next project after that is I've been doing some computer vision that's going to track fruit that's flying through the air. And then I'm going to either build a 2 degree of freedom robot or hopefully borrow a 6 degree of freedom robotic arm that can move fast enough so that, you know where this is going, so that I can attach a sword to the robot as the end effector and have it slice the fruit that's going through the air. So it's like a real life version of Fruit Ninja.
Man.
Oh, wow.
Oh
So
my
if anybody
God.
has like a fast moving 6 degree freedom arm that they want to let me loan, or you know somebody that works at KUKA especially, I'm thinking of their Agilist line of robots, just, you know, just call me. I'm standing by the phone right now.
How many subscribers do you have? If you reach like this like crazy subscriber count, please think of us. We are still down there.
I have just a few thousand subscribers. I only let the best people subscribe.
Oh, cool. So
it's more of an elite thing.
Yeah.
But I think you have to like maybe injure yourself before your subscribers count is going to go crazy. Like lose a couple fingers and then you're going to go viral.
I mean, you're right. Like at the university I work for, they put out a video because they found a treatment for Alzheimer's that is showing a lot of promise. And they put out this video, and in my mind, that's big news. Like Alzheimer's is terrible, and it affects a lot of people, and a cure or treatment is a good thing. And the video got like 100 views. And I noticed when I was watching that video that in the suggested videos, there was a video of a toilet exploding in a cornfield in Kansas, and it has like 1 billion views. And so at some point, you just have to give the people what they want.
Apparently exploding toilets is what they want.
They do love exploding toilets.
Until they have to clean it up.
Well, you do it in someone else's cornfield.
Oh man, that's sad.
It's like that old American saying, never blow up a toilet in your own cornfield.
Okay. That's about it. I think my plans for 22, I don't make many plans. I really enjoyed 2021. I really enjoyed the live streaming. So I started this in August, I think, this weekly Wednesday one-day challenges and small projects, and that kept me doing stuff. That's really cool, and I want to continue that and build up the community. And I'm looking forward to see all your people's projects. And I thank you for joining. Thank you to the chat for joining us today on this really long stream. Not long for my measures, but long for average measures of casts out there. It was a blast, a really cool project. I hope many people feel inspired. So check out the links of the people, follow the social media. And the next MakerCast will be on the first Sunday of February. We have already January. Oh man, this is almost like spring there. Okay. So
we also have a Twitter channel to follow. So if people want to get a notice somewhere.
Yeah, you do. Dave is the manager of MakerCast. MakerCast would have died a long time ago if Dave wouldn't take care of it.
I can't disagree there. But
I think it's linked in the description. I linked to the Twitter channel, so you get the latest updates there. Because it's not the next one is not on my channel. It will be on any other maker out there. So if you are like active on social media and a maker, reach out to us and through the channels, and you can join our group and even host on your channel there. Cool. Thanks everyone. That's everything for today, and we see you next time. Bye.
Thanks for watching, everyone.
Bye-bye.
Thanks.